We've used converges loosely so far. The sample mean settles down, standardized sums approach a bell curve. But convergence of random variables isn't one idea. It's four. And they don't all say the same thing. Time to make each of them precise, and see how they stack up against each other. In probability, for every small epsilon, the chance that x sub n strays more than epsilon from x shrinks to 0 as n grows. Almost surely. The sequence of outcomes itself converges to x, with probability 1. A statement about whole sample paths, not just one n at a time. In distribution, only the cumulative distribution functions converge, at every point where the limit is continuous. The shape settles. Nothing is said about closeness for any single outcome. In LP for p at least 1, the PTH moment of the difference goes to 0. Control not just on typical behavior, but on the size of rare large deviations too. These four aren't equally strong. Almost sure convergence is the tightest. It implies convergence in probability. So does convergence in LP, for p at least 1. Bounding moments is enough to bound probabilities, by Markov's inequality. And convergence in probability implies convergence in distribution, the weakest of the four. None of these arrows run backward in general. The law of large numbers actually hides two separate claims we glossed over. The weak law, the sample mean converges to mu in probability. The strong law, the sample mean converges to mu almost surely, a strictly stronger statement about the entire infinite sequence of averages, not just its behavior at each fixed n. Watch entire sample paths of the running average settle down together. That's almost sure convergence in action. None of these implications reverse. Classic example. A random variable that's usually 0, but spikes to 1 on a shrinking sliver of probability that keeps sweeping around. It converges to 0 in probability, since that sliver's width shrinks to 0. But it never converges almost surely, because the spike keeps recurring infinitely often. No single outcome ever settles down. Convergence in distribution is weaker still. It's silent about any relationship between x sub n and x at the same n. X sub n could converge in distribution to the same law as negative x sub n, and never once get close to it. Four notions of converges. Almost sure, LP, in probability, in distribution, ranked from strongest to weakest, each implying the next, but never the reverse. They're the formal scaffolding under everything we've built so far, the weak and strong laws of large numbers, and the convergence in distribution behind the central limit theorem. Next, the delta method and Slutsky's theorem, how convergence in distribution survives algebra, letting us build confidence intervals and test statistics out of these limits.